Is that correct answer? Not right. Which you got. Like one was pretty much less than one off, another one was like
Don't know why that would be. Let's talk about it. We might be able, I think we'll be able to finish this still, and we can talk. Okay, I'm 30% sure this is set up right.
Oh my God, I need to
That's not very sure.
Well, you know, it depends. Like, you're 30% sure you're going to win the lottery, that's pretty good.
Well, yeah, that's true. That is very high for the lottery. Like, it would be really great if I had all the time to remember 10.
You make a potato battery in junior high or something? You could just...
Yeah, I wish I could do that. No, it looks like I have done that, apparently. I can't submit mine because, like, I'm one of the ones that actually submitted mine. So now my problem
Is it?
I should have just not submitted it.
different numbers.
Different stuff. Can I just email them to you?
Yeah,
Do you have
this time. This one special time.
Okay.
one special?
I appreciate it.
We only have 9 weeks of this class left. It's like, I know that this is only like a semester course, but when we take physics 1 also, it's
It's
really
in
long. Yeah.
Okay. So we had that sort of brief impromptu lab about spring mass systems. And what we were comparing were how amplitude and the spring constant and the mass affected the period. I gave everyone full credit for the lab, but there were not 100% correct answers here. In that the amplitude doesn't actually impact the period. So remember, the period is the total amount of time it takes to go up and back down one time. And if you have a larger amplitude, it has to move faster to cover that same distance in the same amount of time, but it just does. It just moves faster. It does not change the period at all. Yeah.
Oh.
Or I might have frequency on the board, but that's just the reciprocal, right? So if it doesn't change the period, then it doesn't change the frequency. Then I think the other ones were correct, if I remember. So the spring constant, if you have a higher spring constant, does that mean higher frequency or lower? So we can kind of read.
It's harder to pull it down, right? If it has a higher constant. So the frequency is going to be less frequent.
So we'll do two different ones. So this is for a lower one. What's the highest? Is it right? Green. We'll try to get them going at the same time here. So of course it's not going to come down by as much either, but that's not directly what we're looking at. We're just looking at how fast. I may have to put these on the whole separate them. No. I'm strong and independent.
You don't have a degree in this. dollars.
We have to have a degree to put
You
it.
do, you do.
Okay.
Everybody knows.
My bad, guys. I'm sorry. That is my bad.
You don't even have a high school degree yet.
Yeah.
I mean,
Come on, you're going.
I know. I'm sorry, guys.
okay, so there's that one.
I feel like it's more frequent with the higher constant. I feel like it bounces more.
Wait, okay.
Yeah, it's more frequent.
Yes.
The green one.
The green one. So higher spring constant is more frequent. And then we have the same spring constant, but a lower or a different mass. So let me get that one there. So this is going to be the next slide. So same spring constant, but this is a higher mass than this one. Aaron's gonna.
I thought you were gonna listen to.
This happened before. Other thing that's happened before is I've damaged the floor.
Oh, it does.
Okay, here we go. Can you tell at all?
I can't tell anything.
That's fair.
Can you just tell?
Yeah, higher mass is lower frequency. Here, how about we do this together? Where my golden arm is an influence.
Yeah, before I'm probably tired.
Okay, so if they have the same spring constant. Whoa! Man, I was really going for it. Then which one has the higher frequency?
I really can't tell. I think the one was right, but I can't
Yeah,
quite tell.
that's right.
Okay.
Because this one is going almost twice as fast, right?
Yeah, I think it's like double jump is what's throwing me off.
Yeah.
Yeah.
Okay.
Because now it's doing it in
So if we put all those together, we come up with a relationship between these, and we're going to do it with energy. But we can see that higher spring constant means faster, lower mass means faster. And we can kind of figure out what that relationship is. So imagine the spring going horizontally, back and forth. And we're going to look at 3 cases. We're really only going to look at 2 cases, but conceptually we're going to consider 3. So remember this notation here. This dotted line is the equilibrium. And then the solid lines are the maximum and minimum, where it's bouncing between. So essentially the amplitude. And then these arrows are telling you the direction of the acceleration and velocity. And if there's a dot there, then that means the velocity is 0. So, if it's moving back and forth, when is it going the fastest? Where is it when it's going the fastest? See if I can get both of these on at the same time. Either which of the three things that I've drawn, or just physically where is its position when it's where it's moving the
Like,
fastest.
I just think it was picture.
Yeah, that's fine. Which one?
I think it's still
That is correct. Okay. So we'll see. Okay. So if we were to, watch this version of it, you can see, hopefully, that when it's in the middle is when it's actually moving the fastest, because it's being slow motion. It's speeding up as it goes towards the equilibrium. Once it reaches the equilibrium, it's starting to slow down. Exactly. So if we were to graph the energy of this system, the total energy is the same no matter where it is until friction starts playing a role in slowing it down. But if friction is pretty low, like it is for this, then the energy is the same everywhere, and it's just a matter of whether it is kinetic energy or the spring potential energy. So kinetic energy is obviously related to the speed, and then the spring potential energy, as you stretch or compress the spring, as you move it farther from equilibrium, you get more spring potential energy. So if you have it stretched all the way to one side, like this, right? This is the most it's going to be stretched before I let it go. And so that's where the spring potential energy is going to be the largest. And you can also kind of see that from the end, right? When it has gone as far as it's going to go, what is its speed there? 0, because it's slowing down to turn around and come back, right? So the kinetic energy is 0 at the end, and so all of the energy is in the spring potential. And then if you're in between, it's in between. So we can set up our equations to figure out a relationship between the speed that it's going, the spring constant, the mass, and how much you stretch it. So these are the variables essentially in our equation. When we're here, it's all kinetic, so 1/2 mv squared. Here, it's all potential, so 1/2 times k times x squared. That was our equation for spring potential energy, 1/2 times k times x squared. But we know how far it's stretched. That is our amplitude. So that is the x that we're putting into this equation here. And kind of relatedly, the v that we're actually putting into this equation is the biggest v it'll ever have because it's going its fastest. So the equation in between those at every point in time, this equation is true, that the energy is equal to 1/2 mv squared plus 1/2 kx squared. It's just that at the 2 points that we're looking at, when it's going through equilibrium, when it's going to the end, we know both v and x at those locations. So it's convenient to look at them there. So the other thing that we need is, you can't really see the part that's covered up. We need to go back to the calculus that we stopped pretending we're not doing, which relates the maximum velocity to the amplitude. So let me just bring that back up to remind you where that's coming from.
Oh man, look at that blue. It's like
There we go. Something's happening. Okay, so remember when we were drawing the sine wave and cosine wave business? So in the example I gave you, we had the cosine for the position graph. And therefore, derivative of cosine is negative sine. So the velocity graph was a negative sine graph. So, oh my God, what is going on here?
Yeah, I know. It was being slow last night.
Wow.
And my room is so bad. Like, I don't get service. Yeah, like their room is like great. I go in there and I can do my work. Like,
She sits on the same wall that she
Same
does in her
wall.
room. And our beds are
it's
like this.
like literally like my bed is here and your bed is here, like the same. Like, but it's just a wall and it's still I get no service, no Wi-Fi. Like that sucks. And that's my problem.
So we had these derivatives, right? So derivative of the cosine gave us the negative sine, and if you take more derivatives, right? So this is velocity is still what we call sinusoidal. Sinusoidal.
Sinusoidal.
I give up. It's that thing. It looks like a sine wave.
Yeah.
But any sine or cosine would, in the family, be that word. Sinusoidal.
I always heard Grisham say it, and I never thought about it before.
So when we take the derivative of the cosine, we get a function that has what in math we call it an amplitude, but since it's a velocity, we reserve the word amplitude to mean the number of centimeters that we're making it oscillate. And then the word we use for this is Vmax, how big the velocity graph is. And that Vmax is the same as the Vmax that we're plugging in over here. Now, we also found that there was another way to write Vmax, and that's from actually writing out the derivative. So if you take x as a cosine of the stuff, and remember, if you want to have a certain frequency in your sine or your cosine, the equation for that is 2 pi times the frequency times 2. There's radian business is where that's coming from, basically. But you can think, it takes 2 pi for cosine to go all the way from peak to the next peak. And so if I want the time to have gone the correct amount of time to go from one peak to the next peak, that time is 1/3. Anyway, that's what you do. So if you take the derivative of that, you get the negative sign. The a is a constant, so it stays out in the constant up front. And then, because of the chain rule, you are multiplying by 2 pi f. So that means that Vx, or Vmax, is equal to 2 pi times the frequency times a.
And A
Is the amplitude. It's the number of centimeters that you have moved the thing to start oscillation. I say centimeters. It should be measured in meters, but rarely you make it in all in meter. So this equation and these equations are going to be what we combine in order to come to an equation about the frequency of a string mass system. So I've set the energies equal to each other here. I've plugged in the equations for energy that we have. The first one is only kinetic, so we have 1/2 v at 1/2 mv squared, where the v that we're plugging in is the maximum. And then the other side is 1/2 Ka squared. It's got the maximum potential energy. And so if you divide some things, you see that the maximum speed is the square root of these constants. So we have the spring constant divided by the mass. But at this stage, we're multiplying by the amplitude. This is the speed that it's going. So the speed depends on the amplitude. But we're going to take one more step. And that one more step is to set the Vmax equal to what we got with the chain rule. And if you plug that in on both sides, you can solve for this F. The A goes away. This A is outside this one. And so once you have put all that stuff together, you get this equation for the frequency. And if you flip that, if you take the reciprocal, you get the period. Usually things are stated in terms of the frequency. Okay, so let's look at the actual equation and see if it fits our observations. So, if you increase the spring constant, what does that do to the frequency? Increases. If you increase the mass, what happens to the frequency? It gets slower, it decreases. And if you increase the amplitude, what happens? I think Nick said it. It stays the same, right? A is not in this equation at all. It is in the speed equation, but in terms of the frequency, the how many times does it go up and down per second, that does not depend on the amplitude. Which might be surprising, but if we come back over here, man, they're still going. Stop. Okay. Oh, come on. You can do it. Okay. So if we wanted to count how quickly it goes through an oscillation, do they actually have a stopwatch here? Okay. So we'll count 5 oscillations. 1, 2, 3, 4, 5. So about a second per oscillation, 1.1 seconds, I guess. So now we're just going to do the same thing, but we're going to drag it farther away from equilibrium, so the amplitude is larger. 1, 2, 3, 4, 5. Close enough. Especially given that it's having a hard time. Okay. So, you don't necessarily have to go through this derivation, but I did want to show you that there is a way, there is a way to derive it. There's a way of looking at basically just energy, which is somewhat familiar to us from last semester. And then just a tiniest little bit of calculus, we can figure out how it works. Okay, so here we've got 4 springs. We're comparing it to this spring. The springs are I'm pretty sure the springs have the same spring constant, but I'm looking to see if it says that anywhere. Oh, they don't necessarily, right. And they do all have the same natural length of 10 centimeters. So you can tell by how much extra a spring is stretched if it is a stronger spring or a weaker spring. So just as a quick comparison, this spring stretches a 5 extra centimeters compared to whereas spring C only stretches 2 additional centimeters when you put 100 grams on each one. So spring C would have a higher spring constant. So that's what I want you to look at. All right, well, I don't know if I'm ever going to be able to get on Pear Deck there. So let's look at our 3 responses. Okay, so C, D, A, B. Okay. Deleted response. Okay, so these two agree with one another. So let's take a look. So which one is the strongest spring? C. And let's go. Which one has the smallest mass? There's 2, but so why would C be the fastest one? Exactly. So let's right. So it's the strongest K, the highest K, and also among the options, the smaller M. M goes in the denominator, so if it's smaller, that would mean higher frequency also. Okay. What can you tell me about D compared to A, the springs? I mean. But since they are stretched the same amount, that same 5 centimeters, so the amplitude is 5 centimeters. But, I'm sorry, I misstated. These are the equilibrium positions. So you're going to make the same amplitude of 1 centimeter afterwards. This is what I intended to say at the beginning. Who knows if I said it right. But that means that spring D is stretching 5 centimeters if you put a heavy mass on it, whereas A is stretching 5 centimeters if you put a smaller mass on it. So D.
Yeah, okay. Yeah. Okay. What I was doing, what I kept doing was I was dividing all of them, how many centimeters they stretch.
And then, how do you know that? So we got C and D, and then A and B. So what's going on with B? Let's look at that one.
It's got a heavier weight, but it's stretched the most amount.
Yeah.
Also, when you divide it, it's 2.
Okay. I think that's all. Did we get them all?
Yeah.
Okay.
We only talked about
Is that as much for the alphabet as you know?
It's so hard to get.
Yeah.
It's got like, two of the letters in her name.
Yeah, that's all that matters.
Or just AC.
Yeah.
Okay. So I would like to have a lab over this, but I don't know when, if ever, that's going to happen. But you're also going to be gone Friday, right?
Yes, I'm gonna do this.
Oh my God.
So what? Just extra credit for whoever's here. I don't know if that's true or not.
Yes.
I mean, we could all just work together.
I'm thinking about that. It might be a spring thing I can come up with.
Spring for spring break?
Hey!
So they can break springs.
Which happens
Go to a spring.
periodically.
Wait, I know what they can do. They can do the spring lab that I did in my 8th grade science class, where you have two people and you stretch out the spring really far on the floor, and then they shoot the springs back
Oh,
at each
we
other,
can
and they
do
count
That is pretty
We
good.
could.
That's actually very related to the next
So
chapter.
you might get a set to it.
Yeah.
And then you make like a wave, and they they see how far the wave went, and then they see how long it took to travel across. It was a lot of fun. We used
Yeah.
like a really big. Oh no, we used slinkies.
Slinkies.
Yeah,
I
we used
love
slinkies.
slinkies.
But metal slinkies.
Yeah,
which,
metal slinkies.
Which is pretty much close to spring.
oh yeah, absolutely.
So,
Oh my god.
The problem with metal slinkies is they immediately start deforming.
yeah.
Yes.
I hear it.
It was really fun.
What? My daughter won a little plastic slinky, and I played with it. It was stupid. And then she got a metal one for Christmas, and by the next day, it was almost, I won't say unusable, but certainly not pretty anymore.
Yeah, well, I think it's like it doesn't matter how old you are, it's easy to mess up a slinky.
Well,
Without
and no
trying to.
matter how
Even
you're
just like
so
trying to get it
young.
to walk down the stairs,
Yeah.
it'll trip
Yeah,
over
that's
itself and it'll get tangled.
Clumsy slinkies.
It does
Yeah,
get
it's good.
So we call that process we've been studying simple harmonic motion. I mentioned that it applies to spring mass systems, but it really applies to an enormous number of systems, at least approximately. Your car has shocks, which are springs that are damped with some hydraulic business. What's that?
Everything's going.
Well,
Well, I don't think it's damn. I don't think there's shocks up there unless you're in a Jeep. So Jeeps typically have pretty big shocks.
I hope so. I hope so.
And so those are pretty literally spring mass systems, but basically everything on your car is also a spring mass system that, I'm sure Karis's car has random shaking events that happen.
Yeah. The best thing about it is like when you're on the freeway or whatever, and I'm going 90, right? I don't. Okay. And you'll hit a little bump or something. I'm like, oh god.
And then whenever you're turning up the hill, yeah.
Coming to school, when I'm in my mom's car, easy. It's fine. You're in my Jeep, I'm like, good lord, it's loud. And then people think I'm a bad driver.
You're not a bad driver.
I'm like,
You just can't drive anywhere you've never driven.
yes,
Yeah.
because I
You
freak out.
She flips out. She just
I
take the wheel, I'm gonna get out of the car.
Yeah, it's so bad. We were on the phone with that because we were trying to get to the ACT that was. And I was I'm hyperventilating, and I'm in the school parking lot, and I'm hyperventilating.
Keep in mind,
All right.
you had someone else in the car with you.
Oh yeah.
We're gonna finish this.
We don't have to, we can leave.
Okay, so the natural frequency is that thing we just calculated with the 1/2 pi square root of k/gram. And what that means is that if you let a system vibrate, that is the frequency it would like to vibrate at. But there are things that can influence that vibration. So one of those things is what we call damping. So damping is essentially due to friction and air resistance and hydraulic resistance and stuff like that. Friction-esque things. And what damping does is to make an exponential decay in that oscillation. So if you were to just multiply that cosine function by an exponential, that's the function that it would actually oscillate in. We also call this an envelope sometimes, this exponential envelope. And so what you would expect is those vibrations gradually get smaller. But there are basically three regimes in which this damping can happen. I'm going to come back to those. One is underdamping, then you have critical damping, and then you have overdamping. So this kind of highlights all three of them. Underdamping, and these are all basically from an engineering point of view, where you would usually not want something to vibrate too much. But if you have a different system, maybe you do want it to vibrate. So it depends on your situation. But in a mechanical engineering standpoint, you probably don't want the whole car bouncing along the whole time. So these three regimes, actually thinking about shocks is a useful touchstone for this. So what you would like is if your car hits a bump, for the car to go up with the bump and then basically back down and then just be done. The two things that you would not like to happen are you hit a bump and it just keeps on bouncing as you continue down the road. Or you hit a bump and then your car jumps up and then just kind of stays there, which would be fine as long as you never hit another bump. Because then you don't have any more to go. Okay. So those are called overdamping, underdamping, and critical damping. For your shocks, you want pretty close to critical damping. So you see a bump, and then you just go back to equilibrium in a pretty short amount of time. Underdamping is where you just keep on bouncing as you go down the road. And then overdamping is the one where you slam it to the top end of your shocks and then just stay there pretty much, very slowly decreasing. For overdamping and critical damping, there's not really an oscillation anymore. It's not really going into the negatives below equilibrium. Whereas underdamping is pretty close to simple harmonic motion, it just gradually gets smaller. So these depend on what's called the damping constant. We use a Greek letter tau for that because we measure it as a function of time. And if I go back over here, this is a little hard to see. Can we just zoom in? I cannot just zoom in. I'll zoom in on this version. Oops. No. There we go. So that exponential envelope is whatever the original amplitude is. So however far you pull the spring to begin with before you let go, it's the same A there. And then it's e to the minus t divided by tau. So t is the actual amount of time that has elapsed. It's the t that you put into the cosine. And then tau is this coefficient. So if you go, let's say that tau is 2 seconds. I haven't exactly told you what exactly that means. But if you have t is 1 second, so you've waited 1 second after starting this motion going. In this exponential, you have e to the minus 1 over 2. And that would be a number smaller than 1. We could just calculate it. So exponential of -1/2. So if you waited 1 second, the spring would only be oscillating with like 60% of its original amplitude. And if you waited 2 seconds, then it's only going to be about 37-ish% of the original amplitude. So the percentage amplitude that it's still oscillating at decreases with time. And tau tells you, it's kind of like a half-life from radioactive chemistry. So it's not literally a half, but otherwise it's the same idea. It's the 37% instead of 1/2. But every amount of time, every tau of time you wait, it is cut down to another 37%. So if tau is 1 second instead of 2 seconds, so I replace that with a 1 there, how much do you think the amplitude will be reduced?
Will we double the 37 or divide the 37?
You're in the right ballpark. It's times another 37%. So that's going to be something like 10%, I think. 14%. So this is 0.37 times 0.37. So every additional amount of tau that you wait, the more the thing is damped. And so that means, I'll just go ahead and answer, I'll just go ahead and answer this question. A smaller tau actually means more damping, because it doesn't take as long for that damping to decrease the oscillation. Okay. I think I'm reaching my limit. We're all reaching my limit. Okay, so I think we will stop here, and we'll start here. Who's ready to go? I will send out some sort of instructions about Friday. At this stage in time, anticipate that those of us who are here will have class and we'll have some sort of activity to do. That Sydney will miss out on.
Don't worry,
Well, I looked at camera. I say I looked at camera, but apparently I was on that camera the whole time. So Sydney, you just got a view of the ceiling and the screen, though, for the whole class.